right, hello physicists. We are coming to the end of our semester. So in the next 3 lectures, we're going to try to gather up some odds and ends of important things that we haven't covered yet, and then we're going to be doing a bit of review. So in this video, we're going to talk a little bit about how electrical power flows. And so that's going to involve some discussion of AC power transmission, why we use AC instead of DC. And then I want to talk just a little bit about how to generate light, how to generate electromagnetic waves, and finally how energy flows in electromagnetic waves. So last time where we left, and this was over a week ago because we've had our Thanksgiving break, we talked a little bit about how there's this generalized idea of impedance, which is sort of like resistance. So remember, resistance was V equals IR. If we had something like in a DC circuit, if we put a capacitor or a inductor, a capacitor just acts like a brake, so the resistance would be infinity. And a inductor eventually looks just like a wire in a DC circuit, so the resistance would essentially be 0. But in a DC circuit, the voltage is always changing. And because the voltage is always changing, you get the response of the capacitor or the inductor. And so we tried to capture that with the impedance, which was just like V equals IR, except for these different circuit elements. V equals I, and then instead of R, we just use something, we put an X there. And just like resistance, this also had units of ohms. But what was strange about it is that the overall impedance for an RLC circuit depends on the resistance, because that's sort of the OG impedance, the inductive impedance, and the capacitive impedance. And what's interesting is that because the phase matters in a circuit like this, electrical engineers have developed this Phasor notation where you can work in adding vectors instead of adding sinusoids. And essentially what comes out of this is that because the voltage on the inductor leads the voltage that's aligned with the current, and the voltage of the capacitor lags the voltage that goes along with the current. These two can cancel out, and that's what happened when we did a lab with this, where we looked at what happens when you have an RLC circuit. So that was where we had a function generator, and then we put a capacitor and an inductor, and there was some internal resistance there. And then you check what happens to the current at all of those. So, we put an ammeter into our circuit, and at some particular frequency, that current is maximized. And it turns out that the frequency where that's maximized is just where XC equals XL, where the impedance of the inductor is the same as that of the capacitor in its magnitude. And the reason that the current is maximized is that these two essentially are opposing one another. So if you look at how these react, the capacitive reactance essentially gets smaller as the frequency gets bigger. In other words, the current gets, if you just have a function generator and a capacitor, as the frequency gets bigger, the current gets bigger. If you just have this function generator and an inductor, the current gets smaller as the frequency goes up. And so the resonance is sort of where those two meet one another. And so if you set them equal to each other, 1 over omega c equals omega times L, you can find the angular frequency where that's a maximum. So we did that in lab. Now, something that I said in a previous video, but I didn't really spend enough time on it, I think, for us to really appreciate it, is that if we just think about instantaneously at a particular moment how much power is being used by our circuit, it still is just the same old thing. It's the power is the amount of current times the voltage. Okay, so if we just had a in our very simplest DC circuit, we had a function generator and we have a resistor. Our current is going back and forth just along with our V. So this is applying some V. It causes an I that's going back and forth because the V is varying in time, like a V sine omega t, and omega is just whatever it is. It's whatever 2 pi times whatever frequency you pick. Now, what it turns out to be useful is to quote RMS values instead of regular old averages. And the reason for this is that if you take the average, this would be plus, and then this would be minus, and the average of any sinusoidal function is just 0. So we use what we call the RMS value of the current and the voltage and I guess the induced voltage, but let's ignore that for now. Now, I just want to make this point in a little bit more of a concrete way. Let's suppose that you have a voltage that's V naught times sine omega t, right? And let's say that you average that over one cycle. The average voltage then would be from 0 to t, and then you take 1 over t, and you would add up all of the contributions of V naught times sine omega t times dt. Now, what's a little bad about that is that this would just be 0. So what do? We instead take our V squared, take the average, and then take the square root. So that's what we mean by VRMS. And so essentially what we do here is we take 1 over the time, and then we take the average, we're going to take the square root of the average of V squared. So, yeah, as soon as I wrote that down, I thought to myself, I'm going to get in trouble with units here. So let's just be careful. We're taking the square root of the average of V squared. So by the average, I'm going to take 1 over t times the average over 0 to t. And now I'm going to square all of this. So it's going to be V naught squared times sine squared omega t dt. Okay, so now what this V naught is just the amplitude, so I can pull that out and I would have square root of V naught squared over t, and then this would be an integral from 0 to t of sine squared. And remember, this omega is just 2 pi over t times t dt. And it turns out that this equation will just give me, in the end, t over 2. So this whole thing is just the square root of V naught squared over t times t over 2, which just gives me V naught over the square root of 2. So that's where our extra square root comes from in all of these equations. And so just to reiterate this, the instantaneous power loss over a cycle is going to vary. It's going to be dependent on the instantaneous current. So when the current is big, the power loss in that circuit is big. But it's not very useful for us to think about that power that's changing every second, because this is happening many times a second. Like in a standard outlet, you're getting the 60 hertz. So you're getting 60 cycles a second where it's your current is changing directions. So it's not useful to think about what's happening, in 1/60th of a second. It's useful to think about what's happening in a couple seconds. So instead, we think about the average power, which depends on the RMS current. But just to be clear, that RMS current is not the maximum current; it's the average. And when we talk about 120 volts on your wall, that 120 volts is not the maximum voltage that's being applied between those two, the two slots on your outlet. It's the RMS. It's the root mean squared. So if you wanted to get the maximum, you'd have to multiply it by the square root of 2. So about 1.4 times bigger than 120, about 170 or something. Okay, so here's just a quick check. What direct current will produce the same amount of thermal energy in a particular resistor as an alternating current that has a maximum value of 2.60 amps. So if you want to think about this, the value that you've been given is just the amplitude, so 2.6 amps, but the power depends on IRMS, so the P average would be that I over square root of 2 times R. But if you remember, our power in our DC circuit was just the I squared times R. This is not changing direction. And so if you set these two equal to each other, you can go ahead and find out that your I DC would just be your regular amplitude here, and you would have to divide that by the square root of 2. Okay, so that one's just a quick making sure that you're thinking about it. Now, if you've been walking around in our world lately, you will notice that there are power lines strung up all over the place. And you may have seen some of these things, like up on the top of a power pole. This is a picture I just took at the park while I was out with my kids. And you see these little things at the top of poles. And you might ask yourself, well, what is that doing? Well, that is a little transformer. And what it's doing is it is lowering the voltage before it comes into your house. The key idea is that if you have a low voltage, you are going to have a higher current, and higher currents are, in some sense, more lossy. If you have a high current, you lose a lot of the juice, but you sort of want to get those voltages lower so they're a little safer to be around people. So this is the idea of a transformer. You've got, coming in on your wire, you've got some sort of a voltage, and what you do is you wind loops around a piece of magnetically active material, so like a hunk of iron. And you can change the voltage by having a different number of loops on the other side. And what this piece of iron does is that it will convey the magnetic flux from going through one loop to the other loop, and then allow this circuit to continue from having it could be, in this case, this is a low voltage high current to a high voltage low current, or you could go the other way around, and you can step the voltage up or step it down. Stepping up, you'd have a higher voltage afterwards, a lower current. If you step it down, step the voltage down, you'd have a lower current, a lower voltage and a higher current. So those two things go together. Now, I know that me just saying that doesn't really help you very much. So let's try to think it through a little bit more carefully. So what I'm claiming is that you have these two loops, and this piece of iron core is allowing the flux through the first to equal the flux through the second. Now, if we have Faraday's law in place, that tells us that there's a connection between the way that flux is changing and the amount of voltage that we have through each loop. And so what we're going to do is use that relationship to find out how the voltage on of the two coils relates to how many times the wire goes around that hunk of metal. Okay, so what I'm claiming is that at any point in time, the transformer is small enough that you can approximate the flux through the primary as equaling the flux through the secondary. And if that's true, then the time derivative of each side should also be equal. This is the magnetic flux, dPs dt. Okay, now we're going to use Faraday's law, which says that the voltage is related to N times, and it's going to be a minus, but it's always changing direction, so we're going to be a little bit sloppy with the phases here. Okay, so this is Faraday's law. And it essentially says that if we have our minus Vn over, minus the voltage through a series of coils divided by the number of coils will give us the total flux, how the flux is changing per unit time. Okay, so now we're going to put this in on both sides. So we have minus the voltage of the primary over the number of turns in the primary equals the voltage of the secondary over the number of turns in the secondary. And remember, we have this sort of, this is our schematic where we have our hunk of iron that's causing the flux to be, the magnetic flux to be the same. And so we have a different number of turns on your primary and your secondary. If it was the same number of turns, then presumably you would just get the same thing out in both cases. Okay, and so we have a minus on both sides, and then this allows us to solve that our secondary voltage. Okay, we want to solve for this. Our secondary voltage is just the number of turns in the secondary over the number of turns in the primary times the voltage of the primary. Okay, so if we have a higher number of turns in our second loop, we would have a higher voltage, our second than our first, because it's the ratio of the number of turns in the secondary to the number of loops in the primary. If we have a greater number of loops in the primary than the secondary, then we would have a way to step down. So this gives us a relationship that could be true for either you're stepping up a voltage or stepping down a voltage. And so that's exactly what I say here. Transformers can either step up the voltage if the number of turns in the secondary is greater than the number of turns in the primary, or step down the voltage of the number of turns in the secondary is less than the number of turns in the primary. Now, what's interesting is that if we have this power being the same, P equals IV, if we have the power in the primary being the same as the power in the secondary, so the energy is being transferred from this coil to that coil as you have an induced current in it, well, in that case, we can write here IP equals VP. Now, if I want, I can I'm just going to put in VP directly, and then I secondary would be equal to I secondary times V secondary. So if I put in this thing for V secondary, V primary times N secondary over NP, then I can divide out my V primary, and I find that my I secondary is now, I'm going to take both sides by NP over NS, NP over NS. Okay, now I find my secondary current is also able to be expressed in terms of the sort of the inverse of that winding ratio. So if you step up the voltage, you step down the current. If you step down the voltage, you step up the current. So these two things go together, and that's why we essentially want a high voltage when we send that energy along a wire over large distances, because currents cause power losses. They cause the wire to heat up. Okay, so let's just take a quick look at two homework problems. How would we use this? It says a generator supplies 100 volts to a primary voltage, a primary coil. So V primary equals 100 volts. So that's going between plus and minus, but we're quoting sort of a RMS. We're assuming that already. And it has 50 turns. So N primary equals 50. If the secondary coil has 500 turns, what is the secondary voltage? Okay, now what I want you to notice is that NS is bigger than NP. In fact, it's 10 times bigger. And because this is 10 times bigger, that means that our secondary voltage is going to be 10 times bigger than the primary voltage. Okay, so it really is that simple. So here our primary voltage was 100 volts. Our secondary voltage, we're just going to stick everything into this equation, would be 1,000 volts. Okay, so that's all there is to it. Not super complicated, but it has pretty profound implications for the way that you would set up a power circuit. Now, here's a second problem for you to think about a little bit. I'll try to help you set it up. It says a transformer has 500 primary turns, so NP equals 500, and 10 secondary turns, NS equals 10. Okay, so this means you have more loops on the first one than the second one. So the voltage here is getting stepped down. You start out with a bigger voltage, you end up with a smaller voltage. So it says, if V primary is 120 volts, what is Vs with an open circuit? So you're going to go ahead and use Vs equals Vp Ns over Np. That's what you get to use for this. Of course, on your exam, I will give you these. And it says, if the secondary now has a load of 15 ohms, what is the current in the primary and the secondary? Well, using this for part A, you're going to find your V secondary. And then using just your V equals IR, which still, this Ohm's law still works for amplitudes, the amplitude of the voltage and amplitude of the current. This is all still fine. And so it says if the secondary now has a resistive load of 15 ohms, so they give you R equals 15 ohms, and you will have found what your V secondary is. You're going to use that here. You're going to find your I secondary. What is it? Okay, now once you have that I secondary, you will be able to find your I primary. So I guess I should relabel these. You can use this to find C, and then you can use this to find B. So once you have that I secondary, you'll be able to use that right there. You want to find your I primary, but you have your N primary and your N secondary, so you'll be able to do that. Okay, so essentially the moral of this problem is if you start out with 500 turns and go down to 10 turns, you're going to end up with a lower voltage and a higher current. So in that primary circuit, you'll have a lower current, a higher voltage. Now, our power grid is very well designed in some sense to take advantage of these things. So at the power plant, steam is used to turn a big turbine, and then that produces AC power, and then you have what are called transmission substations to increase the voltage for bringing that energy from the power plant to our homes. And then when you've probably seen some of these power substations at different points in a city where you have these high voltage transmission lines that are typically farther up, higher above the ground, and then you bring the voltages down to a more reasonable level that's a little less dangerous. Then you bring them to different points in the city, and then you have another smaller transformer that brings the voltage down another step to come into your house. So I'm no expert in this, but my understanding is that in the high voltage tension lines, the voltages are like 150,000, 700,000, very high voltages. And then when you bring it down to the local level, you're bringing it somewhere around 7,000 or something. So quite a big change at this substation level. And then that is brought down to your 240 volts, which is fed to your house, which is then split into two separate sides of your power box at the back of the house. So there's a whole lot to it, and there's a reason that you have to go get a degree in electrical engineering if you want to be allowed near all this stuff. Now, just as a historical side note, Tesla, whose name you know from our use of his moniker in the for the units of magnetism, invented a lot of what's now our standard power system, this three-phase power system. You'll notice in these high transmission lines you usually have three wires going side by side. That's because they're each carrying a signal that's essentially offset by 120 degrees. So they are all offset. This is a publicity photo that Tesla took in Colorado. He did not sit in the room while they were sparking this. They did essentially a double exposure. But his big idea was that you were going to essentially be able to go beyond the system that he'd already helped Westinghouse develop and just send the electrical signals through the atmosphere. And there's a lot of interesting history behind this, but I think that modern experts are sort of agreed on the fact that the power losses would be a little too great for this to be a very useful system. All right, now, since we are at the end of the semester, we do have to kind of pick our battles. So what are we going to skip? Well, if you were going to take a junior level course in electromagnetism, where you'd probably start is with Maxwell's equations. And Maxwell's equations summarize all of this electrical material that we've been talking about. So we've just been talking about things like Gauss's law and Faraday's law. Those are also legitimate. You'll notice Maxwell's equations include that. Maxwell also adds a Gauss's law for magnetism, which says that there are no magnetic charges. Magnetic fields are caused by currents instead. And all that Maxwell really adds to this whole thing was this extra little piece called, which was called the displacement current in those days, but which we don't need to use those terms. But in any case, he put these all together in a form that was self-consistent. And so all of classical electrodynamics can be summarized in those four equations plus our Lorentz force equation, which there's still disagreement about whether that's an extra or whether you can get that out of Maxwell's equations themselves. Now, I want to also warn you that we're skipping over a whole lot of interesting material on permanent magnetism. The reason is just it's complicated. You have a lot of different situations with magnetism because essentially materials are quite sensitive. For instance, if you have a paramagnetic material, the magnetism is stronger inside them. If you put it inside an external magnetic field, the magnetic field inside of that object will be stronger. It will want to line up with the field. On the other hand, if you have a diamagnetic material, it will essentially the magnetic field inside the material is weaker because the magnetic domains inside of it oppose the direction of the external field. And so you see different effects that arise from each one of these. And also, maybe even most importantly, we have ferromagnetism, which is the sort of the permanent magnetism where the little, the angular momenta of the little tiny atomic components are lined up with each other. And so that allows you to have these kind of permanent magnets that were the things that were discovered the first, but understood sort of the last. So in that case, it's sort of a complicated story, and it took physicists well into the 20th century to really get a grasp on these things and apply them to things like, making VHS tapes and cassettes and all of that. So we're going to skip that because it's hard. And so let's talk a little bit more about something that we have more experience with, and that's light. Now, I want to encourage you that a lot of the stuff from here on out is not fundamentally new physics, it's just applications of old physics. So for instance, if you wanted to make a light wave that has some frequency, you now have the skills to sort of understand what's going on, because we've talked about LRC circuits and what sorts of ways that you could tune your inductor and your capacitor to get what frequency you want. And so you could use that and then use a transformer to increase the current, and then that the frequency would be set by the L and the C, and then your current amount could be set by introducing a transformer, and then you could set up a little antenna that has some wavelength and frequency. So those two are of course connected because your speed of light is the wavelength times the frequency. And it turns out that light can be described in terms of oscillating electric and magnetic fields. Now, as I say, this speed of light is large, but it's not infinitely large. It's about 3 times 10 to the 8th meters per second. Now, all of the different wavelengths of light have the same speed out in the vacuum. That's not actually true in materials, and it's important that it's not, or else you wouldn't have things like prisms. But out in the vacuum, we can just say that all of the different wavelengths of light have the same C. So you can have long wavelengths, things that are, a meter long, or you can have short wavelengths that are about, 100 nanometers long, and that are the sorts of waves that the only types of waves that we can see with our eyes, because the little antennas at the back of our eyeballs, the little rods and cones, are developed for that. So just to say again, we have all sorts of electromagnetic radiation. You can have radiation where the wavelength is shorter than the size of an atomic nucleus, or you can have wavelengths that's the size of the Earth. So there's really a huge range, and our eyes are optimized only to see a very teeny little part of that, but we can use antennas and stuff to sense all the other ones. And this is very useful because it allows us to have radios, and back in the day when people were using TV over the air more. And in any case, all of our Wi-Fi signals are also sort of ensconced in this. Now, we say that light waves are transverse because the electric and magnetic fields are oscillating in a way that's perpendicular to the direction of the motion. Now, if we say that we describe our electric field, for instance, as, the electric field is E naught times sine of omega, or kx minus omega t, in, for instance, the j hat direction. And if we put our b as our b naught times sine kx minus omega t in the k hat direction, it turns out that these two are not independent. Because Faraday's law connects how the magnetic field is changing to the voltage, you can do an integral around a loop and find that the amplitudes of these two are related. And it turns out that E and B are each carrying equivalent amounts of energy, but they don't have the same amplitude, at least in our system of units. The ratio of EM to BM is connected to C, so the magnitude of our E that we get is a lot bigger than the magnitude of our B. It's bigger by a factor of 3 times 10 to the 8th. So I give you a little homework problem to make sure that you understand the difference here. And all I want you to do there is actually use that C. So 2.998 times 10 to the 8th meters per second. So there's going to be a big difference between the magnitude of the electric field and the magnetic field. And just to say it again, which one is going to be bigger? Well, the EM is much bigger in magnitudes, although they don't have the same units. So it's sort of comparing apples and oranges. Now, just one last interesting thing. If you go through Maxwell's equations and think about how energy is being carried by these electromagnetic waves, there's something called the Poynting vector, which relies on the cross product of the E and the B in a system. And this S has units of power per unit area, so joules per second per meters squared. And it's essentially telling you how much energy is flowing through that surface in terms of meters squared. So if you want to find the total energy, you would have to add up over a surface. But you'll notice it depends on E squared. And the reason it depends on E squared is because E and B are connected. So this is just saying this magnitude of S is going to be 1 over mu naught times E times E over C. So that's where that comes from. C times mu naught times E squared. Now there's a very strange and sort of profound thing that comes out of this. And if you go back and look at all of what we've done so far in terms of this Poynting vector, it shows us that the energy in our circuits is not actually sitting inside the wires. The battery creates an electric field that's pointing from the positive end to the minus end. But if you're thinking about how does the energy flow from the battery, for instance, to a light bulb, the energy is not flowing inside of the wires, but it's flowing in the electric and the magnetic fields outside of the wires. So I encourage you to go watch this Veritasium video. I've linked it in your PowerPoint, but if you want to just look it up, The Big Misconception About Electricity from Veritasium, he talks about that a little bit more. Okay, so what have we talked about today? We've talked about how AC voltages are good for transmitting power because transformers allow for current and voltage to trade off. I've talked about electromagnetic waves. You can generate them by accelerating charges. Accelerating charges cause oscillating electric and magnetic fields to be generated, and light is just one type of that electromagnetic wave. And then finally we've talked about how the Poynting vector tells us how the direction of our power depends on the E and the B, and then our thumb would be the direction of that power transmission.